Have you ever wondered what voltage really is? Well, let's unravel this mystery together. Voltage, my dear friends, is the electrical force that moves electrons. It's the invisible power that lights up our world. To make it more relatable, think of a waterfall. The height of the waterfall is like the voltage. It measures how much potential energy there is to get the water, or in our case, electrons moving. Now imagine the water at the top of the waterfall poised, ready to tumble down. That water has potential energy because of its height. Similarly, voltage measures the potential energy that can push electrons from one point to another, creating what we call an electric current. So when we talk about voltage, we're really talking about the force that pushes the electrons along their merry way. So, in essence, voltage is the push that gets electrons moving. Now that we understand voltage, what about current? Let's dive right into it. Picture a river. The current in that river represents the amount of water flowing down its course. Similarly, in the world of electronics, current signifies the flow of electric charge. More specifically, it's about how many electrons are on the move. Imagine standing on the bank of that river, counting every water droplet that rushes by in a given second. That's analogous to how we measure current, by counting how many electrons pass a certain point per second. It's not just about the push, the voltage, but how many players are in the game, how many electrons are actually hustling. So in essence, while voltage is the driving force, the push that gets electrons moving, current is the measure of these moving electrons. It's the traffic report of electrons on the highway of a circuit. So, if voltage is the push, current is the amount of electrons that are actually moving. So how do voltage and current relate to each other? To answer this, we'll dive into a fundamental principle of electricity known as Ohm's law. According to this law, current is directly proportional to voltage and inversely proportional to resistance. Picture this. Imagine a river. Its width represents resistance. The wider the river, the less the resistance. Now consider the river's waterfall height as voltage. The taller the waterfall, the higher the voltage. Finally, the water flowing is our current. So when the waterfall is high, high voltage, and the river is wide, low resistance, a lot of water can flow freely, high current. Conversely, if the waterfall is low, low voltage, or the river is narrow, high resistance, less water or current can flow. This analogy beautifully illustrates Ohm's law and the relationship between voltage, current, and resistance. So, in simpler terms, more voltage and less resistance means more current. Let's sum up what we've learned about voltage and current. Voltage, remember, is the electric potential energy, the force that pushes electrons from one point to another. It's the energy source that drives our electronics, from the smallest microchip to the largest power station. And current? That's the actual flow of these electrons. It's the river that's driven by the force of voltage, carrying energy from the source to power our devices. Like water in a river, the current is the medium that transports the energy. Now, understanding these concepts is fundamental to all things electrical and electronic. It's like knowing the ABCs of a language. Without a grasp of voltage and current, the world of electronics remains a mystery. But with it, you unlock the potential to understand, to innovate, and to create. So the next time you flick a switch or charge your phone, you'll know it's all about voltage and current.